Yes, good afternoon. Good afternoon, everyone. Okay, good afternoon. So, on continuation of our previous session, today we will be looking into arithmetic circuits, data processing circuits. Just confirm, am I audible? I hope I am audible. Okay, thank you. So, we were been looking into the logic gates. So today we will be seeing the arithmetic circuits and data processing circuits. So the first portion of our course will be fully on the components which we need for the coding the Verilog. So we are slowly moving into the designing part. Okay. So the digital system performs mathematical and logic operations. You know, yes, it performs mathematical and logic operations on binary data. These operations are handled by arithmetic circuits and data processing circuits. That is what we were trying to look into, arithmetic and data processing circuits. For example, calculator, microprocessor, which has arithmetic circuits and data processing circuits, DSP processors, ALU, embedded controllers, AI accelerator hardwares. Okay, so these all are the core building blocks in the digital VLI systems. So with these, we will be trying to build our own system. So this is something we have to understand the arithmetic circuits and the data processing circuits, and you should know what is the difference it is getting and all such kind of things. Okay, so in the arithmetic circuits, this is uh, this is nothing we are going to uh, learn new. Okay, the thing is the same: addition, subtraction, and something you have to go and increment it, decrement it, and you have to do some multiplication, comparison, division, whatever in our real life scenario we are doing. Those they converted into an operations so that the machine can do. Okay, so in order to have the arithmetic circuits, these all are building blocks. Slowly, we will try to build our arithmetic circuits with the help of half adder, full adder, then parallel adder, subtractor. Then we'll go for the arithmetic logic units. So, so the main thing is you want to understand what is this operation and how do I implement that operation using the gate. That gate and all we have learned in the previous sessions. Now we are moving further. Okay, we are moving and how do those gates going to act as an arithmetic circuits. So in that there are half adder, full adder, such kind of the circuits we are going to understand it. Okay, so that is an one thing. So let us try to get an something here. It happened. Okay, it is XR. S is XR. Okay, so S is equal to A XR B, and this is AND gate. C is AND gate. A dot B. Okay, so the half adder adds two 1-bit binaries. That means the input we are giving is only two 1 bits. This is 1 bit, this is another bit. Okay, the half adder can add only two 1-bit binary inputs. So that is what the input is A, input is B, and the output you will get sum and the carry. So what are the possible outcomes of 2-bit? Okay, either this you can have this, you can have this, you can have this. When you try to add this, add this, add this, add this, you will get a carry. That is what. So we need someone to take care of carry, and we need someone to take care of sum by having this help. Okay, by having this input A and B. So you see that same value, okay, same input 0, different input 1. That means XR. So A, they'll call symbol like XR B. Okay, next for the carry A and B. That is what the thing. Okay, A and B. I am not going to teach how we got all those things. Through this, you can derive this Boolean equation. From the Boolean equation, you can go on to do the circuits. I am not going to teach that. Just I am giving you an attention that, oh, something you have to learn, something you have to concentrate on these things. That is what the idea. Okay, so here the problem is, if there is a carry and if you do the other if it is where we have two numbers 1 1 something like that. Okay, so this 1 1, the carry is gone over there, this it cannot handle it. That is the problem. So there is no practical use of this half adder. Actually there is no much practical use, only 2-bit, two single bit, one single bit, one single bit, that addition you can do it. So there is no practical implementation, but we need to understand these things so that we can go and understand our full adder. Okay, so by cascading the two half adder, we are trying to get a full adder. We are trying to get an full adder. So a full adder adds 3-bit. It adds 3-bit. So that means there we can give carry also as one of the input to the adder. We can give carry also as one of the input to the adder. So the output you will get is carry out and sum. So this is the truth table. So 3 input. When we try to add all 3, the sum is 0 and the carry is also 0. When we try to add this, sum is 1 but the carry is 0. If you don't know how to write this, then it is really a problem. Truth table is the base, because full adder, we are designing the problem statement. Then from that we have to write, we want to bring the expression. Okay, we have to bring the expression. Here some typical uh, type error. You can see this. Okay, this is the idea. Okay, this is the Boolean expression we got from the truth table. Okay, so we are trying to define the inputs and trying to put those logics in the truth table, and after that we will try to derive the Boolean equation, and from the Boolean equation you can derive the circuit. That is what the things. So here they used two off adder and one OR gate, where you will be able to get the things. So for the sum, it is something like XOR with this, XOR with this, you will get this. Okay, so what is XOR? Same means 0. So 0 you will get. XOR with this 0, we are getting it. Same means 0 and difference means 1, we got it. Difference means 1, we got it. Difference means 1, we got it. So that is the idea. Likewise the carry, you see a dot b is 0, a dot b is 0. Okay, then C in anything and with 0 is 0, that we got it. I'm seeing this equation and trying to get the things. Okay, so by using the truth table we can derive this Boolean expression, and from that we can go and use it. Okay, we can have this circuit. Okay, it is a full adder. Now thank you. 423 423, what is this? Okay, so now so we want to connect. See, one full adder, when we try to connect it with the another full adders, with the help of these we can add 4-bit addition. We can add 4-bit addition, one carry in. Okay, because it gets the one full adder gets the 3 input and you will get one sum. Okay, so it is ripple carry adder. Why? In the sense, 4-bit means, so at a time we will pass this and carry. At the first we will keep carry 0 and then we will push the things, and then for the when it goes to the second gate we will send this bit 2, bit 3, bit 4. So that is the idea. So bit 1 of one number, bit 1 of another number, bit 2 of another number, bit 2 of another number. Likewise it will be coming it over here, and then bit 1 of the carry, it is, we will set as 0, and then once this got completed, when this carry goes inside, from this you will get the result of this, you will get the result, you will get the result, you will get the result. Okay, this is what the ripple effect, what they will call ripple effect. When one takes effect, it will slowly, it will go and hit the things. Okay, so that is where the ripple effects. So 4-bit addition, so each carry ripples to the next stage. Why in the ripples means the carry is rippling here, moving. Okay, from here you will, if he gets the carry, it goes, it goes, it goes, it goes. Okay, and at the end we will get. So this is where you can use it in a practical way. But the disadvantage is it is too slow, and carry propagation delay, because carry want to go here, 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 here. So it is a delay. So the delay increases with bit width. So suppose if you are using 8-bit addition, then again you need 8 flip flops, and it want to go on doing this. Okay. So for that, they introduced something called carry look ahead. The circuit will try to get uh, the carry ahead. Okay. So this is a dot, generation is a dot. 1 second, guys. 1 second. Guys, still now I didn't talk. Okay, I stopped there and I was I cannot avoid the call. That was the thing. It happened. Okay, no worries. I am starting it from. So the carry look ahead. The previously it was an uh, the ripple adder. Now the carry look ahead adder. So it improves the speed by reducing the carry delay. Okay, by reducing the carry delay. So this is a dot b, and then this is the carry g1. This is the generate, and this is the propagation, and then these things. So it is fast, better performance, more hardware complexity, and a high speed processor. So they will go and predict. Okay, the carry, for the carry itself they have the prediction. So with that they will directly give all the bits, and then it will be able to go fast. That is where the carry look ahead. So this actually, there is a typographical error. I will modify and I will send you the things. Okay. So the thing is, in the ripple carry adder, it is something. It is moving in an. I mean, it is rippling. It is time, but this will not take time. It is used in high speeds. Okay, it is of high speed. Okay, so the next thing is subtractor. So now we have been looked into the adder. We looked into the adder. Okay, now we will see the binary subtractor. So it performs subtraction. Okay, so one thing what you can do is you can go and do. Okay, a b, and then give the input, what is the output you need for these things. Okay, and what is the borrow. From this you go and derive the uh, equation, and then you can draw your own circuit. Okay, so here my catch is, what I am trying to tell is, you try to understand this concept. Adder concept, subtractor concept, and again you will come back. The likewise you have an full subtractor. Okay, full subtractor, we have to understand this concept. Next, incrementer and decrementer. Okay, because these and all we will use in program counters, address generators, and loop counters. So when we, okay, so if CPU want to fetch the instruction from the memory, it want to generate an address, then for the next instruction it want to increment by 1, and for the next instruction it want to increment by 1. So for that purpose it is something program counter. So for that we need incrementer and decrementer, multiplier and divider. Okay, I am not asking you to go and by got the things. You just go and recall these circuits which you have been learned in the past, or right now you are learning. Try to give some attention and try to get to understand it. Okay, so it is this application, it is used for this AI accelerator, and then this is mainly used in the processor and signal processing. So why I am telling this is, these arithmetic circuits we will be using it as a module. We will create one arithmetic circuit. That arithmetic circuit we will use it for many things. Okay, we will use it for many computations. So we will write code once and we will try to use it. Okay, so that is the idea behind it. Okay, so what I am trying to tell is, first we will try to create a gate. Using the gate we will try to create the basic operations. Okay, uh, basic operations, and from there we will try to create adder, and using the adder we will go and have, using the multiple adders we will go and uh, create our actual thing like ALU, or the DSP processors, something like an UART. For that you need some calculations, such kind of things. We will go and use that module. That is what I am trying to insist. Okay, so these are some things you shouldn't, oh, this is what, this is what. These are the building blocks which you guys want to keep a note of it. I'm not asking you to by God, keep a note of it. Okay. So with that, we will be able to get the arithmetic logic units. So it is adding, subtracting, incrementing, and decrementing. Okay. So by combining all the arithmetic stuffs, we are able to do one arithmetic and logic units. So it can perform arithmetic operation and it can do the logic operations also, and comparison, and then it can do left shift, right shift, such kind of things where you can go and make use of it. Okay. These are something we will try to do this this in an Verilog. When it comes to the coding part, we will try to go and do these things with the help of first we will try to do these AND gates, and then the add, subtract, increment, and decrementer, and we will try to combine everything and do one basic arithmetic units, so that you will be using all the things what we have learned of the adders, subtractors, and all such kind of things. We will go and use it. Okay. So for that, this is the thing which you try to keep a note of it. Okay. So now, till now we looked into the arithmetic circuits. It is nothing but arithmetic circuits. Now, data processing circuits. Now it is data processing circuits. So these circuits manipulate, route, transform, and select data. Okay. These circuits manipulate, route, transform, and select the data. So what is that? Okay. So it will not compute. See, in the previous thing, computation was happening. Here, it will, whether it want to send the data, it want to change the path of the data. So such kind of things, whether it want to select the data or not to select the data, those kind of operation is done by the data processing circuits. So these all are not arithmetic. Please try to understand, these are all not arithmetic circuits. These are all data processing circuits. These are data processing circuits: multiplexer, demultiplexer, encoder, decoder, comparator, shifter, register, and this ALU. Okay, in the ALU we will use the data processing circuits. Okay, so why I put these things is, please try to understand, you can have, by using the multiplexer, you can derive an adder. That is another concept. And inside the ALU, we will be using data processing circuits. That's why I went and put ALU. If it is confusing, you just try to delete it. That's it. So MUX, multiplexer, what it is doing, what is its purpose? It selects one input among many. How? Okay, suppose there are many things are traveling over here. Okay, and you want to allow only one depending on some condition. So depending on some condition, you can make either to allow I0 or I1 or I2 or I3 depending on this control lines. So you will have one control circuits. Using that control circuits, you can make this as a switch. Okay, these things you can see in an microcontrollers where the GPIO pins will be multiplexed. One pin can act as a input pin or an output pin or an UART TX pin or an SPI SDA pin. So such kind of things you can go and make with the help of this MUX. So they are telling it is an I0, I1, I2, I3 as an inputs, and then this is the selection line, and select lines determines the output. Okay, so that the data is routed, and even you can instead of data you want to select the bus. Okay, then processor data path, Those things are happening. Next, demux, demultiplexer. One input distributed to one selected output. Okay, one input distributed to one selected output. So here it is the reverse of the mux. That's it. Okay, you will get a line and you want to choose in which line it want to go. So depending upon this condition, you can allow whether to activate A, B, C or D. Okay, for memory addressing, communication routing, data distribution. For okay, it is the opposite of mux. Okay. Okay, I got the information. Next, encode. So I want to convert this information into a small, like a binary codes. Okay, multiple inputs into a binary codes. So you can go for. So the 8 line is converted into 3 lines. That's it. Okay. So for keyboard encoding and for interrupt handling, we can go for this kind of encoders. Okay. Then the next is decoder. So whatever we did, we want to get those things. We want to, by using these, the value of this, we will go and decode what is the exact data. Okay, so you will have an encoder and you will be having a decoder. With the encoder you will get these things, and with the decoder and you have a select line with that where you can go and decode it, and here it is going to be encoder stuff. That is what. Okay, so whether you want to select the memory chip selection, address decoding, such kind of things. And even when you try to uh, uh, fetch the instruction, fetching and then decoding the instruction. Okay, so we will try to go and have a bit by bit of what kind of instruction is getting, that is getting decoded with the help of decoder circuits. Okay, I hope you guys able to get the stuffs. Okay, what I'm trying to tell is, this is the CPU, and in the memory we will be storing the instructions. Okay, these instructions are binary encoder according to the ISA. According to the ISA. Okay, see, now I gotten things. Okay, I am just diverting the topic so you guys have a better idea. There is something called instruction set architecture. This is very much important. Okay, the people who are working in the hardware designing, they will follow this instruction architecture for ARM or something like that. The people who want to develop the firmware or the software for this architecture, they are the software guys. Okay, so this ISA will become an intermediary, so the hardware guy don't want to depend on this software. If they implement according to this ISA, this software will work. If the software is implemented according to this ISA, this hardware will work. That's it. So this ISA, this instruction set architecture plays an important role as a middle thing, so that both they all the hardware and the software engineers can go and work independently, where they can go and the chip manufacturer, the chip developer can develop their own according to the ISA. Okay, so that is the idea. So now we come to that part. The CPU we have, and then the memory we have. Okay, so I told no that instruction is compliance to the ISA. So they have 132-bit size or 16-bit size instructions. Okay, the CPU want to understand whether it is a add instruction or an sub instruction, how it is able to understand that. Okay, it fetches, and how that understanding is happening, it want to decode it. That is what, because already while compiling we went and encoded it, now we want to go and decode it. I was trying to give you one example so you guys get an idea about where this encoder and decoder will be used. Okay, that is the things. Hope you guys got an idea about the stuffs. Now comparator. So how the data route and the diverting path and how to encode it and how to decode it, we went and looked at it. Next, in the real life scenario, we have the decision stuffs. Okay, something we have to compare. Always we will compare with others. Okay, so something, if we want to take some decisions, these all are the stuffs which we have to go and do the stuffs. Okay, it is equal to, it is not assignment. Okay, it compares whether a is greater than b, whether a is equal to b, or a is less than b. Okay, so it comes for the decision logic. This is very much important. And to sorting the hardware and the control units, these all are very much important. Depending on the input, whether it is, it want to compare it, and according to the comparison, it want to go on to take the decisions. That is where this is a data processing circuit, not arithmetic or something circuit. This is the data processing circuits. Okay, next, see, it is not always we will send the data like parallelly. Something we have to send it in a serial way also. So we need some kind of shifter. Okay, 1 1 1 0, and we have to make 1 1 1. This is one to shift, this one to shift, this one to shift, so we can send these things in a way. So something we need is such kind of operations also. So that is logical shift, arithmetic shift, rotate, and the application of this is fast multiplication, data alignments. Okay, so for example, these things, if you do a left shift of this, okay, this goes out and this comes here, and you will get this, and it is equivalent to the multiplication by 2. Okay, now the data path concept. Okay, data path is the hardware path where data moves and gets processed. Data moves and getting processed. Okay, so it includes registers, ALU, mux, shifter, what all things we are using now. So it is used. So from the register, ALU, shifter, and it goes to the output. So here, this is the data path. Okay, so how it is managed is the control. We have something called control, and it will go and manage all these operations. Okay, so it is nothing but the hardware path where the data moves. So from the register level, it want to move into the arithmetic operation, you need some path. The path is nothing but a connection. That's it. A path is nothing but an connection. So that is what the data path concept. But you don't think as an, I told it in a small way like a wire. Okay, but they have their own protocols. Please try to understand. Okay, they have their own protocol. If you see the data sheet of the any microcontroller and its block diagram, you can see the bus architecture, and especially in an ARM architecture, AMBA bus, AMBA AMBA bus is that. Okay, and AMBA light bus, they will call it as AHB bus. So they have their own protocol implementation, how to do the stuffs. Okay, so just I'm giving you an overview. Okay, that's the thing. Next, what is the thing with, what are the things we have learned now? What is there any relevance with our VLSI? Okay, so the CPU. Okay, so these blocks form processor internals. Whatever the things we learned till now, ALU needs it, and the CPU is nothing but a bunch of registers, and plus ALU gives you the CPU, and you need multiplexer, comparator, shifter, and arithmetic blocks. Okay, and these we will optimize and make our CPU to run speed and less power consumption and small area. So these all are something building blocks of our CPU. So that is what it is VLSI relevance. Okay, so it is mathematical operation, adder, subtractor, multiplier, divider, and ALU, and it is a data manipulation, routing, multiplexer, decoder, encoder, comparator, and shifter. So just I am trying to give you an what it is doing. So how you can define this block, whether it is a data processing or an arithmetic circuit. Okay, these are all simple only, no problem. Just listen it. Don't want to think much about it. Okay. So in the summary, what I am trying to tell is these we need it. This also we need it to make one full working system. So these are the essential digital building blocks for the modern VLSI design. So we will try to go and implement the code off adder. Through the off adder, we will go and we will not write again an off adder. With the already we created a code for off adder, we will use that off adder to make a full adder. Likewise, with the help of full adder, we will go for these kind of circuits and we will go and do it. Okay. So these are the something which you try to get an idea. Okay. So today's session is somewhat it goes, I know it goes with more stuff. I didn't go much deep inside what is happening inside and what is exact stuff. I don't want to give such kind of stuffs. The goal of this thing is we want to really move into quickly into the coding. So to do what we have to do, simply we cannot go on right straight into the coding. So we want to understand some basics for the system we have to analyze. So that's I was trying to give you the things. Okay. So still 4 to 5 days, you have to be patient. Then we will move into learning the Verilog. Okay, we will be learning the Verilog code. Then you might be feeling little bit hands-on, full of hands-on. So I hope you guys went through the. I hope you guys would have went through the um, EDA stuff. Okay, here I went and used uh, the code for the some arithmetic and logic operations. Okay, it is so easy here to make an ALU. Okay, addition, subtraction, AND operation and an OR operation and the results, and to write the test bench, all such kind of things. I was trying to do the things and I was trying to run and I'm able to get it. That is not a big deal. So you guys, please don't leave it. Try to make a continuous stuff. I mean, put the efforts and go and read the things. uh, I have given you only the gist. Okay, I have given you only the gist, but there are lot of things you have, but don't go deep inside the circuits, how these things are implemented nowadays, not that much. Okay, just try to understand what is happening over there, what is happening, these kind of things. Okay, what is happening, and then try to work it with the code. After understanding it, my thing is you try to put it in the code, whatever the concept you have learned, try to put it in the code and do it. Okay, see, nowadays you please try to understand, use AI tool. Okay, go and use the AI tool. Okay, for example, let me go and make, okay, uh, maybe the ripple carry adder. Let me go and check ripple carry adder. Okay, see, you have to use the AI tool, and you have to integrate the AI tool with your working environment. That is a special art. Okay, that is a special art where you guys want to go and understand. So nowadays the VS Code already it get integrated. Maybe I can show you one thing so that you guys can go and work for any coding purpose. Okay, I use this the code. Okay, here I want to go on explain about the main.c. I'm just giving just this is the project I went and used. Okay, and here somehow in the VS Code the AI is getting integrated. Okay, it is trying to get this idea, okay, from the stuff, the LLM, and it is making us to, and it is giving the things. So it is not necessarily you want to go and remember all the syntaxes and all those things. Nowadays AI, it's see, then once with the LM I'm able to read the whole file. Okay, the whole file I'm able to read, and it is giving me an thing, quick summary, purpose, and then the top level definitions, what are the functions it is using, so that I can go and read the things easily. Oh, this is what is happening. This instead of reading the code, I can make the LLM to go and work with us, to work for us, and we can go and get it. Okay, it is not a sin of using AI tools. That means by using AI tools, someone will think that your mind will getting no, that is not okay. Okay, to you have to see in future you have to use more AI tools. That is very much important. That is what I'm trying to get. Okay, so now I need ripple counter, ripple adder. I think okay, ripple carry adder, ripple carry adder. So the prompt I'm going to give is, okay, I need an Verilog code for the above. Second being, I need a test bench for the above. I will use EDA playground for simulation. That's it. See, you have to give it in a specific way. So it started giving me an Verilog code, and it started giving me the test bench. And if you need, you can go and ask the things. So it is an art. Something if you are interested in learning, you can go and use your LLM, and directly you can go and apply, and you can go and work on it. It is not a sin. Nowadays in companies also they are expecting that kind of stuffs only. So one person want to do many kind of stuffs. Okay, so I am expecting only this from you. You start using your AI tools. Use AI tools as much as possible, and try to analyze what it is happening. If you didn't understand any line, you try to get, so that your understanding gets much better. You don't need any faculty or someone. If we have a basics, the basics is very much needed. Okay, without basic directly, so to use the AI tools and how to get the more efficiency from that, you must know your domain knowledge. That is very much needed. Okay, once you know the domain knowledge and using this AI, it is a powerful tool. So you will be having and you will become more powerful in uh, industries. Nowadays these are the things it is happening in the industry. So you guys please please use the AI tools. Even the developers, they are going and attending and classes for this, for having this kind of stuffs. Okay, so you guys please go and do the stuffs. Okay, so actually that today's thing is, it is not a big topic, so it got a little bit early also. So if you guys have any doubt, please let me know, or else we can wind the session, no problem for me. So please let me know if you guys have any doubt. Yeah, I used it from the Google. I used simply an AI, that's it. See, it is this model, Gemini 3 model. Gemini 3 model. In the Google search itself, you will have one AI model. That only simply I went and used it. For coding and all, it is good. They are telling that cloud, CLAUDE, cloud is good. Such kind of things are good for the AI. Okay. So if you guys don't have any doubt, we will close the session. Okay. So tomorrow, anyhow, at the end, I will start the sequential circuit basic. Okay. After comparator and the, I think a comparator and then priority encoders. Then I will start the sequential circuit. Okay. So up to 10 days, it is fully with the theory part only. Next, then I will go for the Verilog coding. So it will be uh, interesting. Okay, so till that, you guys want to be patiently listen to it. Okay, okay guys, thank you, see you tomorrow, bye. Yes, EDA playground. Yes, it is EDA playground. See, EDA playground, that is what I went and used. Okay, that is EDA playground. Okay, thank you all, bye.